So apparently I hit the wrong button and hit stop on the record as opposed to pause. So instead of starting all the way from the beginning, I decided just to continue on here. So where we had left off, remember, was we had talked about the fact that we have this, how memory works here, where we have these pieces of data. For instance, this 3F, 1A, 25FF, and then that's our actual data. But then we have these addresses here, the 0x00001344, and then we did 1345, and those are like the actual location in memory where that is stored. And so that address is, those addresses are connected into the ALU unit. And the reason we need it in the ALU unit is that the data, like the instruction that's sent over, might say, the opcode might say to, for instance, to add these two pieces of data together. For instance, the opcode might say, hey, I want to add those two pieces of data together. So the opcode would be sending not just adding the two pieces of data, but we'd also be having information like the memory addresses of where that data was located as well. And so, you know, the ALU will then be able to have access to that address to be able to, you know, pull the data from there. Now, we also, you see I have a branch coming here. We have input and output peripherals. Now remember how we have general purpose input and output pins and stuff? Well, there's also going to be addresses for those input and outputs. You got to think of it as like, I always think of it as just like your data is a piece of mail, and you need to know where to deliver the mail to. And every house has an address. So even though, you know, in memory we're saying, okay, well, data stored there. Well, we also have data on input and output devices. Like if you put in a pressure sensor, you're going to be reading in pressure data. So that's got to have an address in order for us to access that data. So that's why we have to have that. And of course, we're also going to have data that's coming from that. But the data here that's coming from this goes straight into the registers, I should say. Or it could be something that's tied as an instruction. You know, because it might be that there's something that the I/O peripheral is telling us to do, so it might be an instruction as well that we have to carry out. So this is one type of overall architecture of how like a CPU with memory and peripherals work, and this particular one is called the von Neumann architecture. Now, what's important to think here is, you've probably maybe heard this terminology before, but I'm going to highlight these paths here. And I'm going to highlight them in different colors. And the reason I'm highlighting them in different colors here is that if we look at this, what we can think of this is that we have a data bus, which is the orange one, and an address bus. So we have two buses. We have two ways of communicating data here. We have just a separate address bus and a separate data bus. Now, there is another type of architecture which I'll let you look up, because I'm going to have a question that you will have to answer. There is a Harvard architecture. Now, the main difference here is the number of buses and that data and instructions are stored in separate memory. Okay, so I'm going to have a question posted that relates to that for the assignment here. So that's the main differences, but you'll have to read on that. And here, I'll give you a hint here. This is, as I said, we're not going to use the textbook very much in this course, but page 5 of your textbook goes into detail on this, so you can kind of see and look at what the differences are. All right, so that's kind of as much as I want to talk about as far as the hardware and how like the CPU is created. So that's essentially what we have, and that what we're going to program. So let me go back to this block diagram here. We're going to write a program, and that program is a set of instructions. And so that's going to be stored in the instruction memory here. And then the CPU is what's going to execute the instruction. And then, of course, the peripherals here, this is what's going to connect up, you know, like our LEDs and our sensors and other things like that. So this chip, this is the chip that we are going to be programming. This is kind of all one chip here. And you might say, what do you mean the peripherals aren't part of the chip? Well, when I say that, I'm referring to those general purpose input-output pins. Those are part of the chip. And they have addresses and they have data. So this is all part of that Cortex-ARM M0 processor that we're going to use. Now, one thing we'll see is like, well, maybe, you know, this might not be the exact correct picture, because I haven't specifically said that the Cortex-ARM M0 uses a von Neumann. It might use a Harvard architecture. So that's something I'm going to have you determine as well. And again, that's something that you can probably find just in your textbook. All right. So let's talk a tiny bit here about I'm sorry, I lost my place there. Let's talk a little bit about registers. First off, registers are typically 16, 32, or 64 bits. That's typically what they are. For us, our registers are going to be 32 bits. So we have 32-bit registers. Basically, the easiest way to think of it is registers are designed so that computations can be done fast. Now, there are two types of registers. There are general purpose registers, and then there are special purpose. The general purpose registers, these are the ones we can use. Whoops. Wrong thing there. I meant to highlight it. We can use the general purpose registers. The special purpose registers, as their name would imply, are for special purposes. So the special purpose registers for our processor, we have 3 special purpose registers. And they are the PC, the LR, and the SP. The PC stands for the program counter. And this register basically tells and keeps track and tells where we go for the next part of the program we need to execute. So for instance, just for an easy example, the program counter might start at 0 because that's where the first instruction is stored, and then once it executes that instruction, the program counter would go to 1 where the next instruction is stored, and then it would go to 2 and so on and so on. Now in reality, it might not be that it starts at 0, 1, and 2 because there are memory is a little bit, we have to be careful because there are memory mapping is a little bit more complicated than, and we're not going to talk about that as far as, well, there are certain areas in memory that are reserved for the program. As far as addresses, there are certain areas of memory that are reserved for the data that's stored, things like that. So it's a little bit more complicated than just starting at 0, 1, 2, and 3, but that's the way the program counter works. The link register this holds the memory address of where the next instruction is that we need to execute. So this is a memory address. Address for next instruction, location. So for location, of next instruction. And then SP stands for the stack pointer. And this holds the memory address for the top of the stack. Now we're not going to talk about stack in this course, that's reserved for a different course here, but a stack is basically kind of, you can think of it as temporary data storage. So instead of storing the data maybe back in the memory where the data is going to be, if you know you're going to use that piece of information over and over and over again, you can push what's called push it onto the stack and then pop it off the stack. There's push pop operations, but we're not going to have to worry about that. Now we want to talk about these a little bit. Now when I say we can use general purpose registers, we're not going to physically program anything to use, let's say, register 0 or register 5. The compiler and program is going to take care of all of that, but what we will be able to do is when we debug our programs, we'll be able to look at these registers and see our data either being loaded into the registers things like that. We can see how the registers operate and how they'll change, which we'll do just so that we can see how these registers operate, and so how we can see that, like a C language program that we write, when we compile it and put it on memory into the CPU, exactly what is happening and what is going on. Okay, so that's what we're going to do. Alright, so that's about as much as I think I want to cover in this particular video. So just to kind of remind you, this video, part 2 of this, was the fact that we finished our computer architecture. And we talked about registers. And that's all we covered in this video.